Okay, modeling. So what are the governing equations? So this is where you think about what are the governing equations, boundary conditions, and initial conditions. So again, what we're looking for here is to look for the simplest model that captures all of the physical aspects of the system. So in particular, you're looking because you're looking for the simplest thing. You're looking to exploit symmetry. So if you see that something's fourfold symmetric, only simulate 1/4 of it. If you see that something is a bunch of repeating unit cells, like I don't know, a heat sink with a bunch of fins in it, if the fins are spaced periodically, maybe you just like simulate one fin instead of simulating 100 fins. Remove unimportant features. So I don't know, maybe there's like a little bump on, like maybe there's like a little slit on one of the fins or something in that system, but we don't think it's an important effect. Maybe you could remove that, and that has the effect often of simplifying the meshes that you end up making for finite element and CFD models. So the coarser you can make meshes and get solutions and get verified solutions, the the faster those solutions are going to come and the more simulations you'll be able to do. So removing unimportant features, geometric features, is really important. Also, removing unimportant effects in the physical model are important. So like if you don't think that thermal expansion is an important part of your heat transfer problem, then remove it. Similarly, like compressible flow can be hard to simulate. It adds a lot of extra complexity to the solution process. If you don't have a compressible flow problem, treat the density as constant. If you think that you have a low Reynolds number flow, maybe like you remove the effect of inertia in the problem. So basically you can, in the flip side of that, if you don't think that if you think that inertia is the only important thing, sometimes you can remove viscosity in the problem, but generally not. If you know ahead of time that from your pre-analysis that the flow is likely not to be laminar versus turbulent, you can remove the use of turbulence models in a CFD simulation, and that'll generally produce better solutions that cost a lot less computational time to get. So pre-analysis is really the key for a lot of those things, is doing some initial calculations by hand or maybe with some light computing before you ever attempt a problem. So like, for example, in our flash diffusivity simulation, I am not going to try to simulate, I generally would not try and simulate something where the thermal properties like thermal conductivity depend on temperature. I know that those probably aren't important because thermal conductivity doesn't depend on temperature very much, unless you have extremely wide ranges of temperature in the system. And so, if I'm only using small delta T's in my analysis, then I can not have thermal or temperature dependent properties, which effectively means that the models that I use get to be linear instead of nonlinear. I can, by using the fact that by neglecting natural convection and radiation and removing those from my model, that means that I can use simpler boundary conditions like adiabatic boundary conditions in a flash diffusivity simulation. Similarly, like by exploiting symmetry, I go from a three-dimensional problem where temperature is potentially a function of radial position, theta, and z in cylindrical coordinates. I can move to a quasi one-dimensional situation where I have temperature as a function of just say like the depth and time. Let's see. I can instead of I've made the assumption sometimes that I'm not going to model the mechanical support for that little disk in the flash diffusivity simulation. Maybe that's important. I don't know, but I won't know unless I do the easier simulation, and then maybe later I'll try and do a more complicated one that has the mechanical supports. Assuming shapes for the initial conditions are all part of coming up with your model.